In this talk, I am not going to attempt to explain any physics to you. I think Francois Englert has done that very well. So I'm going to tell you just a personal story about my part in the theory, how I came to do it, and I won't be showing you any equations or diagrams at all. So I shall just talk, and the text is there in case you can't follow what I say. So I've called my lecture "Evading the Goldstone Theorem" because that was the technical problem that I was most concerned with. And my story begins in 1960 when I was appointed lecturer in mathematical physics at the University of Edinburgh. And before I took up my appointment, I was invited to serve on the committee of the first Scottish University Summer School in Physics. I was asked to act as steward at the school in July, my principal duty being to purchase and look after supplies of the wine which was to be served at dinner each evening. Now, the students at the school included 4 who stayed up late into the night in the common room of Newbattle Abbey College, where the school was held, discussing theoretical physics, and they rarely got up in time for the first lecture the following day. They were Dr. Nicola Covibo from Rome, Dr. Sheldon Lee Glashow, at that time coming from CERN, who later shared the 1979 Nobel Prize, Mr. Derek Robinson from Oxford, and Mr. Martinus Veltman from Utrecht, who shared the 1999 prize. Many years later, Covibo told me that their discussion had been lubricated by bottles of wine collected after dinner and hidden inside the grandfather clock in the crypt. Now, I didn't take part in these discussions, perhaps unfortunately, since I had other things to do. And consequently, I did not learn about Glashow's paper on electroweak unification, which by then had already been written but was not yet published. So, after the school, when I took up my duties as lecturer, I was in search of a worthwhile research program. In the previous 4 years in London, I'd rather lost my way in particle physics and had become interested in things like quantum gravity. But symmetry had fascinated me since my student days, and I was puzzled by the approximate symmetries, what are now called flavor symmetries of particle physics. Now, these are the symmetries I should emphasize involved in the strong interactions of particles. And then in 1961, I read the papers by Nambu and Goldstone on models of symmetry breaking in particle physics based on an analogy with the theory of superconductivity. And Nambu's models were inspired by the Bardeen-Cooper-Schrieffer theory based on the Bose condensation of Cooper pairs of electrons. Francois Englert has already talked about condensates in other circumstances, but in superconductors, that is, in the old-style superconductors, metals and alloys, the condensate is something which is a spin-zero object, but it's composite, built out of electron pairs. And on the other hand, Goldstone wrote models using elementary scalar fields with a wine bottle potential, sometimes called Mexican hat, but given my history in failing to conserve wine, I prefer to use the term wine bottle. And Goldstone used this potential to induce Bose condensation which was very like what happened in the earlier account of superconductivity given by Ginzburg and Landau as long ago as 1950. And what I found very attractive about the program was the concept of a spontaneously broken symmetry. That is, the idea that the underlying dynamics is fully symmetric, so it's a real symmetry, if you like, but the observed phenomena are asymmetric, and it's a consequence of having an asymmetric ground state, or vacuum, as we call it in quantum field theory. So it was, to me, an attractive idea because it was a nice way of understanding why these flavor symmetries would be approximate and not exact symmetries of the phenomena. Now, most particle theorists at the time didn't pay much attention to the ideas of Nambu and Goldstone because quantum field theory was out of fashion. Despite its success in quantum electrodynamics, it was failing to describe either the strong or the weak interactions in particle physics. For the strong interactions, it was a matter of a quantitative failure. The calculations just didn't give the right experimental answers. But for the weak interactions, it was far worse. It was just that there wasn't a consistent kind of theory to account for them. The other thing I should say about the theoretical climate of the time, the attitude of particle theorists to this work, was that they tended to view condensed matter physics as another country, nothing to do with them. And at a Cornell seminar in 1960, Victor Weisskopf remarked, and this was recalled by Francois Angler's collaborator, the late Robert Brout, particle physicists are so desperate these days that they have to borrow from the new things coming up in many-body physics, like BCS. Perhaps something will come of it. Now, there was an obstacle to the success of the Nambu-Goldstone program. Nambu had shown how the spontaneous breaking of a chiral symmetry, that's where the symmetry acts independently on fermions spinning one way and fermions spinning the other way. He'd used a model of spontaneous breaking of a chiral symmetry to generate masses of spin-half particles. Like, well, for him, they were the proton and neutron because at that stage, people didn't know about quarks. But in his model, there were massless spin-zero particles. They looked as if they ought to be the pions, but they were massless, contrary to experimental evidence. And as noted by Steve Weinberg around that sort of time, any such particles would dominate the radiation of energy from stars, which we understand as being largely electromagnetic. And anyway, the experimentalists would have found them very easily, so they really couldn't exist as massless spin-zero particles, and this was a defect of the Nambu-Goldstone type of theory. Goldstone argued that such massless particles would always be the result of excitations around the trough of the wine bottle potential, as Francois has described. Now, in 1962, this sort of intuitive idea of Goldstone's was elevated to the status of a theorem by Goldstone's Salam and Weinberg. I understand that it was Salam and Weinberg, inspired by Goldstone's ideas, who wrote the paper, and Goldstone agreed at the last minute to have his name included amongst the authors. And the theorem said, in a manifestly Lorentz invariant quantum field theory, if there is a continuous symmetry under which the Lagrangian is invariant, then either the vacuum state is also invariant, or there must exist spinless particles of zero mass. Put more simply, if you want to satisfy the requirements of Einstein relativity theory and you want to spontaneously break a symmetry under a continuous transformations, then you inevitably have these Goldstone zero mass particles. And this theorem seemed to put an end to Nambu's program as a candidate for real physics. So the question arose after that paper, is there any way of evading this theorem? And I think the first hint that it could be done came from the condensed matter theorist Phil Anderson, who appeared as one of the authors writing about superconductivity on one of Francois Angles' diagrams. Now, Anderson wrote a paper in which he pointed out that in a superconductor, the Goldstone mode becomes a massive so-called +1 mode due to the long-range Coulomb forces, and this mode is just the longitudinal partner of transverse electromagnetic modes, which are also massive. That is really the statement of what is now called the BEH mechanism, but how it works in a superconductor where the dynamics is not relativistic. And then Anderson remarked, the Goldstone zero mass difficulty is not a serious one because we can probably cancel it off against an equal Yang-Mills zero mass problem. That is, he speculated that this would work just the same way in a relativistic theory. But he didn't show that there was any flaw in this theorem which had been proved, and he did not, in fact, discuss any relativistic model. So particle theorists such as myself received this remark with some skepticism. And then in the following year, in March '64, Abraham Klein and Ben Lee suggested that even in relativistic theories, a certain equation which was crucial to the proof, for the proof of this theorem, could be modified by the addition of an extra term of the kind which certainly existed in condensed matter theories. And in June, in a reply to this paper, which appeared in Physical Review Letters, Walter Gilbert, who was at the time in transition from being a theoretical physicist to being a molecular biologist, for which he later won a Nobel Prize in chemistry, Walter Gilbert ruled out this term as a violation of Lorentz invariance and said you can't do that. And it was at that point that my intervention took place. I read Gilbert's paper on the 16th of July, 1964. It had been published a month earlier, but in those days, the University of Edinburgh's copies of Physical Review Letters came by sea. I was upset because it implied that there was no way to evade Goldstone's theorem. But over the following weekend, I began to recall that I had seen similar apparent violations of Lorentz invariance elsewhere in no less a theory than quantum electrodynamics, as formulated by Julian Schwinger, one of the winners of the '65 Nobel Prize. Quantum electrodynamics, as Francois has already, I think, said, has a property of being invariant under so-called gauge transformations. And these are transformations which make the setting up of a quantum version of the theory ill-defined, and you have to fix the gauge before you can have a well-defined quantum formalism. It was fashionable to do this with a Lorentz gauge, which is one which doesn't violate relativistic invariance in any way. But that gauge has certain unsatisfactory features. It doesn't really fix things completely. And Schwinger preferred a so-called Coulomb gauge, which is one in which you fix the gauge in your own inertial frame of reference and decree that happens for all eternity. And that's a real gauge fixing, a complete gauge fixing. And it was well known that this choice of the gauge didn't lead to any conflict between the predicted physics and relativity, even though fixing the gauge in this way led to apparent violations of relativity in some of your equations. And Schwinger, as recently as 1962, written papers in which he demolished the folklore which had grown up, the folklore that it's gauge invariance alone that in quantum electrodynamics requires photons to be massless. And he provided some examples of properties of a gauge theory containing massive so-called photons, but he hadn't given any explicit underlying dynamics. So he didn't actually arrive at the VEH mechanism this way. And during the weekend, following my reading of Gilbert's paper, it occurred to me that Schwinger's way of formulating gauge theories undermined the axioms which had been used to prove the Goldstone theorem, because the formalism was no longer manifestly Lorentz invariant, and the axioms then didn't apply in a gauge theory. And so gauge theories might save Nambu's program. And I wrote a short paper about this the following week, which went to Physics Letters on the 24th of July and was accepted for publication. By then, I'd written down the classical field equations of the simplest illustrative model that I could imagine, which is just the result of introducing electromagnetic interactions, in other words, Maxwell, into Goldstone's very simplest scalar field theory model, one which was illustrated in Francois Angler's slides. And it became obvious that then, just writing down these equations, that when the symmetry was spontaneously broken, the Goldstone massless mode disappeared and became the longitudinal polarization for what in the quantum version would be a massive spin-1, photon or vector boson anyway, just as Anderson had suggested. So in other words, what I'd really done was to prove that Anderson's somewhat speculative remarks were correct. So my second short paper, which consisted of a brief account of this model, was sent to Physics Letters on the 31st of July, and it was rejected. And the editor at CERN suggested that I develop my ideas further and write a full account of this work for Il Nuovo Cimento. And I was indignant about this. It seemed to me that the referee had just not seen the point of the paper. A colleague who was at CERN visiting during the summer when the paper arrived later told me that the theorists there didn't think that my work had any relevance to particle physics. And besides that, it seemed a little odd that the earlier paper, which was essentially just a mathematical remark, had been accepted, but the more physical follow-up had not. So I decided to augment my paper by some remarks on possible physical consequences, and also to send the revised version across the Atlantic to physical review letters, where I hoped the referees would understand it better. And amongst the additional material was the remark, it is worth noting that an essential feature of this type of theory is the prediction of incomplete multiplets of scalar and vector bosons. Now, the scalar incomplete multiplets of scalar bosons, meaning massive spin zero particles, was, I think, really the only justification for the way in which my name has become attached to the particle which was eventually discovered at the LHC. So it was essentially an accident which followed on from the rejection of the rather shorter one side of A4 version of that paper. So the revised paper was received by physical review letters at the end of August and was accepted, and the referee invited me to comment on the relation of my paper to that of Englert and Brout, whose paper, which had been received in June, that is essentially most of a month before I'd even come to grips with the problem, and their paper had been published that day. And until then, I'd been unaware of their work, because to me, the theory group in Brussels was essentially a condensed matter theory group. They didn't work in particle physics, as far as I knew. And I added a footnote to my paper as soon as I saw a copy of theirs. 20 years later, at a conference in 1984, I met Yoichiro Nambu, who had started all this program, and he revealed he'd been the referee who had accepted both papers. So just a postscript. It took some time for the work of Englert and Brout and myself, and of Geralnik, Hagen, and Kibble, who published a little later, to gain acceptance. In fact, amongst most particle theorists, it took quite a long time for anybody to take any notice of it. My longer 1966 paper was written in autumn '65 at Chapel Hill, North Carolina, where I was spending a sabbatical year at the invitation of Bryce DeWitt. I think his name is slightly. Yes, I'm sorry. His name's I think. Oh no, there it is. It's okay. Bryce DeWitt, and the invitation from Bryce was a consequence of my interest in quantum gravity, and I think he was very disappointed that instead of working on quantum gravity, I was continuing to work on this, what he probably thought was a load of nonsense. A preprint which was sent to Freeman Dyson at the Institute for Advanced Study at Princeton, received a very positive response. He complimented me by saying my paper explained a number of things which he had previously not understood, and he invited me to give a talk at IAS Princeton. And in March '66, when I gave the talk, I faced an audience including axiomatic quantum field theorists who still believed that there could be no exceptions to the Goldstone theorem. However, I received a polite reception, and I learned afterwards that I had convinced at least Arthur Whiteman, the leader of the group, that what I'd done was right. So the next day, I gave a talk at Harvard. This had been arranged by my friend Stanley Desser of Brandeis University, whom I'd met at a conference before I crossed the Atlantic. And that was addressed to another rather skeptical audience, which included Walter Gilbert. And the seminar, style of the seminar was very different from the one in Princeton. It became more of a dialogue between me and the audience than a talk from me alone. And some of the people in the audience knew more about this subject than I did and were very helpful in adding additional explanations. And so I survived the seminar, and the work was accepted as valid. Though later, when I met Sidney Coleman again at a conference in 1979, he told me that he and his colleagues had been looking forward to this seminar at which they would tear apart this idiot who thought he could get round the Goldstone theorem. So there again, there'd been a rather strong belief that the theorem was really universally true. So after the seminar, at which Shelley Glashow was present, he complimented me on having invented, as he said, a nice model. But he didn't recognize its relevance to his electroweak theory. So there was another missed opportunity. I remarked at a talk I gave in the Hérichet Summer School when Glashow's 60th birthday was being celebrated in 1963, that missing the opportunity then was why Shelley had to share his Nobel Prize with those other two guys. So like Nambu, the six of us who published in 1964 expected to apply our ideas mostly to broken flavor symmetries of the strong interactions. That was what the Nambu program had been set up originally to do, and it was amongst particle theorists there was a lot of attention was given to these broken symmetries of strong interactions, but very little attention to broken symmetries in the electroweak sector. And Glashow had been one of the pioneers in taking this kind of symmetry seriously, well, along with Sidney Blotman, who'd published a different model 2 years earlier. We, that is the Gang of Six of 1964, tried to, or some of us tried to apply the work to strong interactions, but it didn't work, and it was left to Weinberg and Salam in 1967 to find the right application, which was to essentially to bolt on the generalization of the model that I had formulated onto Glashow's electroweak theory, discarding the explicit mass terms. So 4 more years passed before Gerhard Toft, in an extension of Tini Feldman's program, proved the renormalizability of such theories, and another 2 before the discovery of weak neutral currents indicated that Glashow's electroweak unification was the correct one. And in 1976, Ellis, Gaillard, and Nianopoulos at CERN encouraged experimentalists to look for the massive spinless boson that the theory predicted. And that was the beginning of what became the big experimental search, which culminated in the CERN announcement in July of last year. Thank you.
So thank you, Professor Higgs. I will now also call on Professor Anglais to come up to the stage here. And why don't you?